please. And we're going. So it looks like most of you have already done the reading assignment for 10.3. If you haven't, it's due tonight. And if you don't get it done on time, then get it done and send me a message that you did it. Otherwise, I added a few more Khan Academy assignments. And I've been trying to be more clear about what I'd like you to do. I'm trying to get used to it, and so are you. But mostly they have really good videos that I've enjoyed lately. As usual, the video exercises are optional, or videos are optional, but then there's exercise sets. I should have made a note. Each of these has 7 questions and they're repeatable. And this one has 7 also. And basically that's 14 total, so I'm gonna give you 2 points per question. So if you answer all 7 correctly here and all 7 correctly there, then you earn 28 points. And I'll just look at Khan Academy and then copy your grade over. So there's no submission required from you, it's just I have to go take a peek to make sure you did it eventually. And this only covers about 1/3 of what's in our textbook. And after a few days of looking, I have not found any other resources yet that cover the other stuff in the book that we can easily do online. If we were in the classroom together, we could pull it off, but I haven't been able to figure out how to cover the other stuff. The other stuff that's in the book is related to maps and how we take a sphere, a map on a sphere, and make it onto a flat paper. That is, I mean, think about trying to wrap a ball with wrapping paper, right? It overlaps in weird ways. And then if you were to slice a ball open, try cutting it so you can make it perfectly flat and unwrinkled, right? It just doesn't work that way. So people have to use some pretty ingenious math to try and make a map on a flat piece of paper from an entire globe. It's easy for small sections of a globe like Oregon or Pendleton, but not for the entire globe. And the book goes over a little bit of that. I'll keep looking to see if I can find some good videos about it. But as far as homework exercises, I really don't have, I haven't been able to find anything to do that we can pull off on the web. What we can do, however, is play with the basic ideas about what is a space figure. And so we're going to focus on just the first half of this section, 10.3. And you just get to read about the map stuff for now. So oops, magic pen, come on. Sec. Come on, there you go. All right. So for 10.3, which is called space figures, we're going to just pretty much focus on polyhedra. And they're kind of like 3D polygons. They have polygon faces. And straight edges. That's supposed to be a plus. And then there's also some almost polyhedra. And one thing that you may end up doing is trying to do some 2D drawings of these 3D objects. So for example, think about the tetrahedron we made in the circle folding exercise. So I'm going to try and draw my best tetrahedron here. Oops, that last line didn't go so well. That's a little better. So if it's like that solid paper object we made would look kind of like this at first glance, and there's some faces that we can't see. So usually what we do is we draw some dotted lines for that. And so on this one, there would be this dotted line connecting these 2 vertices back there to get the 4 faces. And so just to double check the faces that we see here, I'm going to switch to a highlighter. So there is this face in the back here that I see. Okay, and let's say that's the first face, counting in the back. So that right there is face number 1. And then down here at the bottom, so just imagine this is made of glass, right? And I can kind of see through it. So down at the bottom there, switch colors, we have this face down here. So let's call that face number 2. And then we have this front face over here. So now my colors are gonna start to overlap a little. Actually, let's stick with the pen and switch to red. So we have this face right here. So that's gonna be, say, face number 3. And then we've got this side face over there. Let's try green for that one. So this thing has 4 faces here, and so tetra is like, think of the game Tetris. That's related to 4 squares. This has 4 faces, so this could be called a 4-faced polyhedra. Or polyhedron for singular. So polyhedra is plural, and polyhedron is singular. Other names we gave it, we called it a tetrahedron the other day. Tetrahedron. Oops, that has to be a D. Back to my pen. Those are all the names I can come up for it. So this is actually a polyhedron, and the one we made was a regular polyhedron because all of the edges were the same, all of the faces were the same, all of the vertices had the same number of edges coming out of them, and then all of the angles between each face were the same. And I'll talk more about that in a second. This could also be called a pyramid. About that. And in this case, it would be more specific. It's a pyramid with a equilateral triangular base. Compared to like the Egyptian pyramids. Let's see if I can draw that. Come down like that, over and over, and back up, and then down here-ish. And then we'll use red for some of the other ones. And then there's going to be this point back here, and then dotted lines for the ones that are in the background. So this would be more like an Egyptian pyramid. So let's switch to green. This one right here, so that's that one. This one would be also a pyramid with a, in this case, I was trying to make a square base. Okay. And these are each polyhedra. Now, as far as almost polyhedra, I put that title in the wrong spot. Let us move it. Down here. So here's an example down here of an almost polyhedra that's related to these guys. If I had what starts to look like a pyramid by making a pointy top, but then instead I make a circular base, okay, then this is no longer a polyhedra because I have a side that's not a polygon. A circle is not a polygon. It's a plane figure, it's just not a polygon. A polygon has to have line segments for its edges, where this has one circular edge. So this would be called a cone. And a cone is also a type of pyramid, which is kind of cool. So we'll also be looking at some almost polyhedra type shapes. And one example of is a cone. Other types of shapes we're going to take a look at that are polyhedra would be called prisms. And so if you think, does anybody remember using the word prism somewhere and what it was for? I'm gonna get a less squeaky chair.
I remember rectangular prisms, but I don't remember where that's from. I just remember the word.
Yeah, so a rectangular prism is a box, like something you get from Amazon, you know. It's got rectangular faces. And if I try to draw a 3D version of it in 2 dimensions, right, here's me trying to draw a box, right? So this would be a rectangular prism. And also it would be, yeah, just we'll call it a rectangular prism. Rectangular. Anybody ever have any memories of prism in somewhere they've seen? Or we can just call it a box. Box. Rectangular prism sounds cooler. So I'm just going to do a quick search for it on the internet and see if this looks familiar. And I have Khan Academy open in the background, and it keeps trying to refresh, and it's freaking me out. Okay, go away, Khan Academy. All right, so show desktop, and then just search for the word prism. And what often pops up is this thing that light goes through, and it takes white light and breaks it into its colors, different colors, and that's kind of often where a prism is used. So let's see, Wikipedia. And the classic one I remember when I was a kid was like this one right here. And it's kind of hard to, that one's a tough one to look at. I'm trying to figure out which way it's heading. Oh, I think I see it. Okay, so this is the top right here. Okay, so this is the top, and this side's facing us, and the triangle is pointing away from us. And so this line here connects the bottom, and it would connect up to the top over there. So I'm going to attempt to draw that. So one thing I'd like to challenge you to do is try and draw some prisms in Pyramid on paper. And we're going to do more with this later when we get into chapter 11. So let's see, I'll try to draw this in a couple of different ways. If I try to draw it the way they showed it, there was this front rectangular face we were seeing. And then there was a triangular top. And then to draw the other sides, I'm going to use a different color because I need to look through the object. So there's this face that matches the top one. And then there's this line that connects them down that way. Okay, so the dotted lines means I'm like looking through it. And the solid lines are the ones I see head on. So some things about a prism is prisms generally we say they have a congruent top and bottom. Congruent and parallel, but it doesn't have to be that way. But for this we'll do it parallel, top and bottom. Right, so this would be one of my tops, and then down here is my other bottom. And you flip it, right? It doesn't matter. And then usually we want from there is we want perpendicular faces from the top and bottom. So that is this face that we're seeing out front here meets at a right angle with the bottom face. And same thing at the top. It meets at a right angle with the top face. So if we were sitting this on the table with the triangular side down, then this would come straight up out of the table at a right angle. So this figure up here, this would be, say, the top, and there's a bottom that matches. So if I draw in some see-through lines, then there would be a line coming down there. There'd be a line, an edge, excuse me, coming over this way, and then be another edge coming over that way if we could see through it. And we're going to play around with these figures a little bit more today. And there's all different kinds of prisms. You can have any kind of base you want. So a prism is anywhere where you have this congruent and parallel top and bottom. Congruent means exactly the same shape. no bigger, no smaller, same angles, same side lengths, same area. And then the perpendicular faces coming up from that. And so if our top and bottom are polygons, then the faces are always going to be rectangles on the side. So I could have, say, a pentagon, oops, color, I could have a pentagonal prism. And what that would mean is that the top and bottom are pentagons. And wish me luck drawing this. So I'm going to make a pretty simple pentagon that looks like a house. And I probably should have slanted those a little bit. Let's try like that. And it doesn't have to be a regular one, but then coming down from here, we have to go straight down till we get to the bottom. Straight down till we get to the bottom. And we have to come off at that same angle because we have to come straight down till we get to the bottom. And then there would be some dotted lines where this vertex comes straight down, straight over, and then this vertex. There has to be a line coming straight down so I can go straight over. Whew, that's challenging. So I have this pentagon at the top, and I have this other matching congruent pentagon at the bottom, and they're parallel, and then I have faces perpendicular coming up. Now, it turns out we can extend the idea of a prism a little bit. So I'll make a cute figure. Oops, wrong way. That's an almost prism, because I'm going to skew the rules a little bit. I'm going to make a thing called a parallelepiped. Parallelepiped. And think about a parallelogram. A parallelogram is like kind of a squished rectangle. And so a parallelepiped is a kind of a squished box. And so here's my best attempt at drawing a parallelepiped today. So I would have like the front face, instead of being a rectangle, would be a parallelogram. And then each side coming off that's going to be another parallelogram. And then opposite sides are going to be parallel. So there's going to be, this is the front face here, and that's the top face. So there'll be a parallel congruent face on the other side, a parallel to this top and congruent underneath. And then there's the sides coming off here, which would be more parallelograms. And if I just use a different color to try and sketch in the sides we can't quite see, they would look something like this. And so that would be a parallelepiped. It's an almost prism because the sides aren't perpendicular, and I did not draw that right. This does not go straight down, does it? Let's undo a little. That's got to come down at the same angle. So that's got to be like that. So there's a vertex there, and then we head over. That's a little bit better. If you squint, it doesn't look too bad. Like a glass cup. Oh, sorry, I just saw your comment, Giselle. So let me see. Is that like these are like a glass cup? Is that what you're referring to? Sorry, I have the chat in a different screen, and sometimes it doesn't catch my attention. But I think that's what Giselle meant. And yeah, so these are kind of like a glass cup. Like I have some jelly jars at home. Oh, I should have brought one. Where the sides of the glass are all these straight faces. And I've counted it once before. I can't remember now. My recollection is it was like a 16 gon at the bottom. My first question on what a prism is. Yeah, a prism is like a glass. No, wait. Yes, a prism is like a glass cup. So another kind of almost prism would be a glass cup with a round base. So let's go over here. So if I have a round top and then the sides come straight down, right, that could be a glass cup. Dotted line coming around to finish that circle. So this would be called a cylinder. And I did not spell that right. And so a cylinder is an almost prism because we do have that, that parallel top and parallel bottom, and usually they're congruent, right? And then we have this side that comes straight down from it. And a cylinder is even more so. If you imagine that this is like a can with a label on it, if you take off the label of a cylindrical can and you unroll it, what you get is a rectangle. So this face coming around here, if we cut it and unwrap it, is just a rectangle, where this height right here is this height right here. And then this circumference at the top becomes this width across there. So the width of the rectangle is the circumference of the label, which I always thought was a wicked cool relationship. So there's lots of prism type things in our life. And there's a few pyramid type stuff in our life that comes up, like cones. I use a cone in my kitchen sometimes when I'm pouring certain liquids from one thing to another. And we'll discover some other cool relationships between prisms and pyramids. We won't get to them until later. What I want to take a look at next is an activity I posted. So if you all could join me on the course homepage here, and let's go back home. And I kind of posted them in a strange order. Here we go, so week 6. I have this activity called Cool Polyhedra, and that's one you're gonna do on your own. And I'll come back to that in a minute. For now, I wanted to take a look at the faces, vertices, and edges, oh my. So if we open up that, this is related to one of the examples in the book that they asked you to get started. Which example was it in the book? In the book, they didn't give it an example number like they usually do. It's near the end of the section. It's called the problem solving application. But I've got it pretty much set up here. So what we're going to do is we're going to look at these polyhedra. And for example, let's take this pyramid over here. And this pyramid has, we counted earlier, 4 faces. We didn't count the edges. So those are the line segments that where the faces meet. And then there's the vertices where all the edges meet. And so we're just going to look at these things and count the faces, edges, and vertices. And sometimes that's a little tricky, and you'll see, you'll have to help me through this in a minute. So we're going to get it started together right now. So I link out to what are called the Platonic solids. And the Platonic solids are the regular polyhedra. And for a polygon to be regular means you have the same length edges in exactly the same angles all around. Okay, so like a square is a regular quadrilateral. So these have a bit more, and let's take a look at the animation here. So you can see it spinning there. Every single edge has the same length. Each edge meets every other edge at the same angle, and each pair of faces meets at the same angle. Every vertex has the same number of edges coming out of it. So pretty much any characteristic you can describe for one edge or one vertex or one face, all of the other faces and vertices have to have exactly the same properties. If that's not true, it's not called regular in the 3D world. And the crazy thing is in 2D, there's infinitely many different kinds of regular polygons. There's a regular triangle and a regular quadrilateral and a regular pentagon. There's only one regular pentagon, right? We can make it bigger or smaller, but there's pretty much only one. There's a regular hexagon. When you get into 3D, and this is the crazy thing, it blew my mind years ago. Why don't you go back? Come on, you can do it. There are only 1, 2, 3, 4, 5 regular 3D polyhedra. Okay, so it's kind of weird. In 2 dimensions, there's infinitely many. You pick the number of sides, we'll make you a regular polygon. In 3 dimensions, There is a 4-faced one, a 6-faced one, an 8-faced one, a 12-faced one, and a 20-faced one. There is not a 10-faced one. There is not a 16-faced one. There is not a 5-faced one. Does that mean there aren't 5-faced polygons? Well, no, there certainly are. I drew one just a little while ago. For example, check out this pyramid with a square base, right? This pyramid with a square base here, come here, pen, is actually has the square base, right? And then coming up from each edge of the square base is 1, 2, 3, 4 triangles. So altogether, this has 5 faces. So we could call this a pentahedron, penta for 5, like pentagon. Hedron, because it is a 5-faced polyhedra. Okay, so this could be called a pentahedron, in addition to be called a pyramid with a square base. But it's not regular, because maybe these 4 triangular faces might be congruent. They're not congruent to the base, right? So it's not regular. Every face has to be congruent to every other face. Every edge has to match every other edge. Every vertex has to be identical in the way the edges come out of them. And it turns out there's only 5 of them. So what we're going to try and do is we're going to try and look at each of these and count the number of faces they have, the number of edges they have, and the number of vertices. And it turns out for polyhedra, they're always related. And so we'll check that out here. So get out a piece of scratch paper and let's do this. So I am going to copy this into my whiteboard. Actually, make sure I have a clean page to put it in. Escape. Next, and new page. And what we're exploring here is called Euler's formula. Polyhedra. For us, it's activity 10.3b. Let me grab that table. So you can just make a table like this on a piece of paper. I'm just going to copy it to my digital paper. And the relationship column is going to take a little bit of work to figure out, but we can easily do the other ones. So the tetrahedron we just did, it's a tetra, right? So the tetra part means 4, so it had 4 faces. So I'm going to fill this in. It had 4 faces. As far as vertices, I got to look back at it and count. All right, so let's see. We have 1 on the top here. I count vertices. Let's see, let's use a red highlighter maybe. So I have 1 on top, and then the triangular base gives me 1, 2, 3 more. So it looks like altogether this has 4 vertices. And then we have to count the number of edges. And so if we go back, if I start here at the top, there's 1, 2, 3 edges coming down, and then there's 3 edges in the base, so 3 and 3. It looks like it has 6 edges, and please correct me if I make a mistake, because I do. And so altogether it had 6 edges. And so we can't really get to the relationship yet, because we got to get some more patterns here. And whatever relationship holds for these 3 numbers should hold for these 3 and those 3 and those 3. So let's do the cube next. So I'm going to draw my best 2D version of a cube here. So let's say I'm looking at it almost head on. Maybe it would look something like this to the best of my artistic ability. And then I'm going to do dotted lines or dashed for the ones I would see through if I had Superman X-ray vision. All right, so let's count faces here. And if you beat me to it, chat or speak up. So let's see, I've got this, let me use my laser pointer instead. I've got this front face here, and it has a matching back face. So I have a front and a back, And then you can say I have two sides. So front, back, side, side. That's 1, 2, 3, 4, and then a top and a bottom 6. That sound right? Anyone want to object to that or correct me? I believe it has 6 faces. So let's see, if it has 6 faces, then in addition to calling this a cube, I could call it a hexahedron. Like kind of like a hexagon, but 3D version. Okay, vertices. So that's all of the points where things meet. A vertex is where 2 lines meet. And so I'm going to actually color those red maybe. So I have 1, 2, 3, 4 on top, and then I have a matching 4 underneath. So 5, 6, 7, 8. All right, we have 8 of those. And then the edges we've got to count. So I'm going to actually switch colors to keep track of them. 1, 2, 3, 4 on the top. 1, 2, 3, 4 on the sides, and another 1, 2, 3, 4. So I had 3 sets of 4, which looks like 12. Okay, so another way to think about it is the top has 4 and the bottom has 4, and then we have to connect the top and bottom. Yeah, 12, that looks right. Okay, and then it turns out there's a relationship for these top 3 numbers that matches the relationship for the bottom 3. And if you see it, so try not to search for Euler's formula, then you take all the fun out of it. This is like a suspenseful movie, right? Octahedron. All right, let's take a look at that. So for that one, I'm not going to draw the octahedron today. I'm going to go to the Platonic solids page and click on the octahedron. So let me see what happens if I click the 3D model. Does this one let me drag it? Some of these you can drag. Oh, this one doesn't drag. What's this do? View or download? Okay. Really, that's octahedron. Oh yeah, I see how it's the octahedron, but I need to rotate it. Okay, so that one's not useful. I thought some of those rotated. I must have to get the animated one. Octahedron, animation. Okay, so this one's moving around. Can we stop it? Doesn't let us stop it. Okay, that's making me dizzy. All right, let's go back. No, stop. And what we're going to do is just blow up in this version here. What if I go to this page? Okay, so we can kind of see it here. Okay, so help me out here. How many faces do you think the octahedron has? Oh no, they tell us on this page. Don't look. Open a new tab. Okay, here we go. I think I see 1, 2, 3, 4 on top and 4 on the bottom, 8, hence octahedron. Okay, so the faces aren't too bad. How about edges?
I think double.
Double. Okay, so I'm gonna copy this so I can draw on it. Get it all. Got it. All right. Add to. Let's go to new page. All right. So let me see. Edges. So it had 8 faces. So 8 faces. Edges. Edges. There's 1, 2, 3, 4 on top. There's going to be a matching 4 on the bottom, and then there's the 4 around the middle. You doing that right? I think I got them all that way, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, it looks like 12 to me. 12 edges. And then vertices, those would be all these points. So there's 1 at the top and there's 1 at the bottom, and then it looks like there's 4 around the middle of it. So that's what, 4, 5, 6 vertices? Does that look like it did that okay? I think so. It's going to get more interesting in a minute. Okay, so octahedron appeared to have 8, hence the name octahedron. Vertices, that was the last one we did, that was 6. and then it had 12 edges. Oh, so it's kind of like the cube, but the faces and the vertices switched. Interesting. All right. Dodecahedron. Dodec means 2 and 10. 2 and 10 is 12. So if we look at the dodecahedron, we should see it has 12 faces. So let's get a new page to put that into and get a picture of it. Back. You want the dodecahedron. Okay, so here's the dodecahedron. So it has pentagonal faces, and my claim is that there's 12 faces here. And it's kind of like a stained glass version of it here. So we have this one face here, and 1, 2, 3, 4, 5 coming around that. And then all of those kind of like have mirror, 3D mirror images on the other side. So 5 plus 1 is 6, and another 5 plus 1 plus 6 is in the back. So do you believe that this has 12 faces, 12 pentagon faces? Somebody give me a thumbs up or a yay or a, you're out of your mind, Parker. Thumbs up, thank you, Olivia. Okay, so we got 12 faces there. And then I'm going to screenshot this sucker and see if we can get, so the next thing we want to try and figure out is how many vertices and edges it has. So that's our next goal. And that's going to be a little harder. All right. So let's see. In the table, what does it call for next? I think it called for vertices next. Okay, so vertices are all the points, right? And sketching this by hand is rather difficult. So I have 1, 2, 3, 4, 5. And then if we go around its midsection, 6, 7, 8, 9, 10, 11. There's one down here, 12, 13, 14. And then I think the next row over here, 15, 16, 17, 18, 19, and I feel like I missed one. Oh, I did, right there, 20. Okay, so we have 5 in front, 5 in back, and 10 around the outside. 5, 5, and 10 is 20. I think there's 20 vertices. Any confirmation or objections to that? You guys still with me? I need to change my background to something more exciting. Definitely gonna get a less squeaky chair. Yeah, this is a hard one to count, I agree. See if this chair's less squeaky. It's just squishy, okay. And then once we get that, we gotta go for the edges. All right, so I'm pretty sure about the 20 vertices. And then I'm going to use the highlighter to do the edges. I'm going to try to guess by counting. So I kind of think the front and the back, I have the 5 edges here. Getting 22. Okay, so we're going to go back and double check here. So let's see. The way I was kind of scheming these is I was thinking there was this front-faced pentagon here. So based on just that pentagon, there are 5 vertices coming off of that. And then as I was looking out here, each of these vertices heads down the side toward the back, but then it's slightly, notice the pentagon behind is twisted slightly. They don't come off in the same spot. So the back one also has 5 edges coming out. So then I believe, like if I start counting here, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 around the belt, you know, the edge, the middle of this, the equator. Think of that as like a wiggly equator. So I think I have 10 vertices on the equator and then another 5 in back. And this one was front. So whenever I did these, I tried to kind of like name the parts so I could make sure I was keeping track of stuff. So I think there are 20 points that make this up still. 5, 10, another 5. Yeah, I'm going to stick with the 20 here. All right, edges. So we've got, let's see, I got my highlighter on. Yeah, I can kind of see that. So 1, 2, 3, 4, 5 in front. So let's make a note. That's kind of hard to see. 5 front. And these are edges. Okay, so then coming off those, mute me, sorry, can you hear me? There we go. There's going to be one, oops, what happened to my highlighter? There we go. 1, 2, 3, 4, 5 coming off the front. So then there's going to be 5 more off the front. And then if I jump to the back, and I think I'll switch color highlighters, let's try a red one. In the back, there's 1, 2, 3, 4, 5. And then coming off of that, there's going to be 1, 2, where did I go? 3, this is becoming hard to see. 4, 5. Okay, so, but I don't think I got them all yet. So I've got 5 edges in front, 5 in back. There's 5 coming off of the front vertices, and there's 5 coming off of the back vertices. But then we've got that whole equator coming around the outside. So the equator, switch highlighters, let's try blue this time. And this is getting too messy. Let's make a new copy of this sucker to get those. Let's see. Let's put it on a new screen. Okay, so here's that shape. So I got the front, the back, and the ones coming off those, but what I missed are these ones coming around the equator of it. And I don't have a highlighter, so that would be 1 to there, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like there's 10 edges coming around the equator, if I did that right. So back here, 10 around equator. Okay, so if I jump in here, that was the 10 coming around. So notice that this vertex, let me get my laser pointer. My first go around, this vertex was not, this edge, sorry, was not accounted for, nor was that one. I got the front face, so here's the front face there. It's kind of hard to see it through that red highlighter. So there's 5 around there and 5 coming off that front face. And then we have a mirror in the back. There's 5 edges around back with 5 coming off each of those back vertices. And then we have these edges coming around the back zigzagging. And you know, another way you could check this, I don't know if any of you have games at home. A lot of games come with dice of different sizes. So let's go back. So I have several board games at home, and the board games have a tetrahedral die in them, and a regular cube die, an octagonal die, a dodecahedron die, and a 20-sided dice. So there's 20-sided, 12 sides, 8 sides, 6 sides. They also have a 10-sided one, but the 10-sided one isn't a regular polyhedron. It's slightly irregular. All right, so if you happen to have some dice like this at home, you could try and look at your dice and count them. And you can actually build these out of like toothpicks and glue, or toothpicks and frozen peas or marshmallows or something. I'll try to do that for the next class. Okay, where'd I go? Where's my notes? And we are out of time. Let's finish this part up. All right, so what do I got here? I've got 5, 10, 15, 20, 30. Is that right? Oops, that's not a pen. I think there are 30 edges, if I did that right. All right, so let's go back to our worksheet here. And where's my worksheet? There it is. So what was it? Dodecahedron was 12 there. Vertices was 20. And the edges was 30. And what I'm looking for is a relationship that these three numbers have, and then the three numbers underneath have the same relationship. The three numbers underneath have the same relationship. The three numbers underneath have the same relationship. In other words, there's a formula that all four of these shapes fill. And we didn't do the icosahedron, we ran out of time. So I want you to try and do that one on your own. Now my apologies, that is the hardest one, but we'll double check with each other on Wednesday. Does anybody see like an arithmetic way to relate 4, 4, and 6? And the same arithmetic relates 6, 8, and 12. And the same relates 8, 6, and 12. And the same arithmetic 12, 20, and 30. They don't all add up to the same number. That's close to the relationship. Okay, so we're going to leave it hanging there for a moment. And so what we're going to do next with this is we'll see if we can find this relationship. We'll see if we can figure out the icosahedron numbers. And I'll confirm those in the next class. And back here. Then what we're going to do is once we think we found that relationship, we're going to come up with 3 other polyhedra, and they could be anything you want, but not these shapes here. So for example, one that might be a good one for us to pick to put in here would be that Egyptian type pyramid, because that's not any of the regular shapes. So back here. Yeah, so this Egyptian pyramid is different than the regular polyhedra, so I could check the faces, vertices, and edges on that. And then let's see, another one we could do would be like the pentagonal pyramid or this triangular pyramid. The rectangular box is pretty much the cube just stretched out, but these two are different than the regular polyhedra. And then we're going to come up with one more. Now that relates to the other activity I wanted y'all to do, and this one's more of a creative one. What I'd like you to do is find a cool polyhedron somewhere. And it could be anywhere. It could be something you've seen somewhere else in your travels. Like maybe you saw some cool sculpture and you realize, oh my gosh, that sculpture was a polyhedron. And then you could describe it for us. Maybe you have a picture of it, or find something online. Maybe there's something in your house or your yard that's a polyhedron that you think is wicked cool. And so this is a discussion forum, so that means we all get to see the posts of everybody else. And then the other thing, so all I need here is you just find a cool polyhedron, give me some kind of reference about where you found it. If it's on the web, I would like a link. Why do you think it's cool, right? Well, what about it was cool? It was pretty, right? Whatever you think, and that's up to you. Another question, and this is kind of optional down here. I guess I should mark this as optional, but I'm curious to get a little creative. If you have any free time, which I don't. Can you build it? So for example, I mentioned when I was looking at the platonic solids, in past classes, what I usually do is I bring in tons of craft stuff and I try to have you guys build with me these shapes. And sometimes we build them on a paper. Other times I bring in like little metal rods and soldering irons. glue guns and skewers. People have made big marshmallow skewer versions of these things. And sometimes people make other more creative things. For example, let's see, do they get into any other aspects of polyhedrons here? They show some cool properties about them down here. They show some other versions of them. A lot of weird math that we don't care about. Oh yeah, these are kind of cool. These dual polyhedra, which are pretty neat, where you kind of take the same polyhedra and you rotate it so it projects through itself. So this is right here, the tetrahedron merged with itself but rotated. Could we build that out of paper and glue and tape and stuff? And then there's things like these that are molecular versions. Oh, here's the dice I was talking about that I have some games that came with those. And then there are a whole bunch of polyhedra that are not regular. So if you just did a search in Wikipedia or elsewhere for polyhedra, like remember all those crazy tilings we looked at, and some of you did some irregular ones? There's all these other kinds of polyhedra that aren't regular but are wicked cool. So maybe one of these grabs your attention. And there's tons of them. There's just like, I don't know, I'm sure there's infinitely many. Some of them have crazy names, like where's the Archimedean ones? Where are those? Those are wild. I thought I saw that here somewhere. I swear I just saw it and I lost it. Anyway, I'll show you the Archimedean ones later. And there's a ton of other cool ones. But so find some kind of cool polyhedron out there. And again, maybe it's in your house, it's in your yard, you see it online, it's a sculpture somewhere, it's something you saw downtown somewhere, whatever. And tell us about it. Send a picture if you can. And so that's just pretty much a relatively easy discussion topic. And if you can build it, bonus for that. So I'll gladly offer a bonus for building some cool polyhedron that you've seen somewhere. All right, so only 2 short assignments in Khan Academy, and then this assignment here, where you just find some cool polyhedron and tell us about it, preferably show a picture, and then we'll finish up this Euler faces, vertices, and edges on my problem next class. So take care, do good math, stay well, and I'll see you in the near future. Bye-bye. Unless you have questions for me.